All right, we learned how to use the bond dissociation energy table in this activity we just finished. We're going to apply it towards the exam question on this page. This is the biggest exam question on test 3. Look for lots of examples. They're easy to spot. They look like this and they got like 6 boxes or 4 boxes or whatever. Question A is the nastiest little single point in all of this course. You got to do 3 levels of thinking first. Okay? Before we start thinking, I'm going to give you a little preview. You can't always say this, but in this particular reaction, you can. The more exothermic a reaction, the faster the reaction. You can only do that statement when this thing called entropy is negligible. And entropy is randomness. Reactions that create randomness are driven by entropy. My favorite one is combustion. You're making all these random gas molecules from fuel, right? Gas molecules have a lot of entropy. They're random. They have more places to be, and they're moving faster. You don't have to understand much about entropy. In this chapter, you have to understand even less. Entropy is roughly 0. There's no change in entropy in these reactions. So we're using delta H, which is called enthalpy. That table gave us numbers for delta H. For steps, we can use steps to predict the enthalpy of the overall reaction. If they're linked, there are steps in reactions. If they're linked with each other, they can be added up for the overall reaction. There's this guy named Hess who developed that thinking process for that. But he had you memorizing equations. There's no memorizing equations here. You're memorizing one fact. Well, it's on the previous page. Instead of memorizing equations that we can get backwards so easily, that's two facts, but really it's one. If breaking bonds is endothermic, I think you can predict what your prediction would be if it was making a bond. So I know it's 2 facts. Okay. So activity 1, we're going to do parts A and B only and circle the major product. You've got 3 questions to answer before you can even circle A. You want them in order? They have to be done in order. Question 1. Which HX happens fastest? Remember, I said the more exothermic a reaction is, the faster it is. I need the delta H for formation of HI, and I need the delta H for formation of HCl. They are on the previous page. HI is right here. Why do I say negative 297? Because you're making it. It's a product. HI was one of the potential products. It is being made. That is exothermic. You put a minus sign in front of this number for making HI. Negative 297 for all the HIs. Negative 297. I'm not going to write it for all of them. All 3 of them are the same. HCl is a bigger negative, isn't it? Negative 431. Which one happens a lot faster? Faster. I should put a green circle on it because that's 1. That's 1, isn't it? Hey, cross off these products. Just based on question 1. HI doesn't form as fast. Given a choice of making HI or HCl, you're going to make HCl because it's happening faster. Okay? Question 2 in blue. Which CH breaks faster. Now think about it. The one sentence I told you to predict speed is the more exothermic reaction is faster. So now we're going to compare two endothermic reactions. Can I give you two random examples? Say I'm comparing a positive 340 to a positive 290. Which one's faster? The one that's closer to being exothermic. How's that? That makes the sentence that I said earlier relevant now too. The one that's more exothermic is faster? Well, if you got two endothermics, neither one of them's exothermic. Which one's closer to being exothermic? This one or this one? The lower one. So here's your question. In blue, I need an energy to break this bond, which would make the first product down here. Do you agree? I need the energy to break the second one, which would make the second box. I need three energies, people, to answer question 2. And I'm going to find them. Give me a category for the first H that I did on the left. I just figured out my shirt here writes on the screen, and it does funny things. I'm sorry. The dangers of wearing a dress shirt to class. Okay. I have a primary carbon here. Okay? Primary. And a secondary here. Are we okay? And a tertiary here. Let's just get those numbers. They're going to be 3 in a row, aren't they? No allylic here. There's no double bond. You don't worry about allylic at all, right? Okay. So primary, 418, 402, 389. I can't do that. 418, 402, 309. 418, 402, 389. What's the sign when you're breaking all of them? Positive. I'm going to be real clear. I'm just going to put the positive. You don't have to put a positive, but yes, we had a question? Which one's breaking a lot faster? I can ignore the other two. Tertiary broke faster. Okay. Tertiary broke faster. So 389 indicates the final product, right? In blue. And then we're going red. 3. DTW said 3 questions. But we only needed 2 here to change color. That's interesting. But we only needed 2 here. We made a decision. I'm going to leave you with an exercise, a review day exercise. Find an old version of this question where a third question had to be answered, and we will do that one. And the third question, I'll tell you, which CX bond forms faster? And you only need to answer that if 2 of the products came from the same carbon radical. You have no idea what I'm talking about. It's okay. Don't worry. Just look for an example, like a worked example even, where you look in the key, and there's a third question there. This is what he was talking about. Let's do that one. But right now, we're finished. Question 1 and 2 did it for us. And the other numbers are all irrelevant. So, you know, I got to make sure. I'm going to cross them off. That one's irrelevant because it's higher than 389. This one's irrelevant because it's higher than 389. 389 happens first. Good. That was a lot of work for that. That's A. A, we did it. B, provide the mechanism for the initiation and 2 propagation steps. We have no idea what that means because we didn't learn this yet. And it's an entirely new mechanism. Nothing like you've seen before. So just, what do you call it? Tabula rosa. Your mind is a blank slate right now. Just absorb. And what you need to do in initiation step, this is part B, part B. Initiation involves breaking the halogens in half. Oh, we have a name for that. What kind of reaction breaks the bond in half? Homolysis, yeah, or homolysis. It depends on how you want to say it. I like homolysis because it's got the two parts separate. And ICL, I want to point out, ICL is the weakest bond on this page. Can we prove it? Give me a number for ICL. There it is. That is a lot lower than any number we wrote down so far, right? 211 will be the first thing breaking if heat is turned on. Yeah. So you're going to turn the heat on for the initiation. That's what gets the game started. The mechanism is very simple. Half the bond goes there, half the bond goes there. Getting rid of my stray dots. Very radical page here. I dot plus CL dot. That is an easy step to memorize, isn't it? Okay. Initiation is, as it sounds, it gets the ball rolling. It starts the process. It's a little spark that gets the reaction going. I like to think of it as the match for a fire. What do you do when you light a fire? Do you light the match and put it in the fire and hold your hand there till the campfire's out? That won't be a pleasant experience, trust me. Once you get it started, the other reactions keep it going, right? Well, that's what propagation's all about. Propagation is keeping things going. Phylogeny recapitulates, progeny is a form of propagation. I don't know where that came from. Propagation of the species. That's keeping your species going, right? So we're going to keep this reaction going with propagation steps 1 and 2. Propagation 1. You got to use the halogen that's going to get an H. Now, you've already answered that question. Which halogen gets the H based on what you circled? Cl. Copy the Cl dot. Which hydrogen needs to be taken off of my organic molecule to make the product I circle? The tertiary one. And here's the deal, everybody. The chlorine meets up with the H, and the other half goes onto the carbon, and you get H bonded to Cl, and you get a carbon radical, don't you? A nice tertiary carbon radical. And HCl is one of your products. So that part is done, the HCl part. Now I got to make that carbon radical into the carbon that has an iodine. So some of you want to hook it up with the iodine you didn't use in your initiation, right? You said, that would make life so easy. That would stop this reaction and you would have a terrible yield. Propagation 2, and I'll leave a little room. You're going to take the carbon radical this time, and you're going to do a reaction like the one you did above. The I is bonded to Cl. What? I thought we reacted ICl. Without further information, you should be very confused right now. How can you have ICl? I reacted ICl. You could say excess, but that's not quite the story. You're getting closer though. There's an I. Say it again. It's not about equilibrium either. Here's the story. Here's the story. What you do is you turn that heat on for a very short amount of time, because I want any radicals I make during this mechanism to be surrounded by molecules that are not radical. So the fact is, you only had the heat on long enough to react less than 1% of the ICL. You have 99.99% left. Let's just say less than 1/100th of 1% of the ICL is gone, which is like 0, right? So you still have pretty much as much ICL as you started with and as much alkane as you started with as well. And the reason is I want radicals reacting with non-radicals, and I want the propagation steps becoming a cycle. Let's talk about it. The activity is over, and now I'm going to talk about what's really happening. So in an extreme world, I'm going to pretend 1 molecule of ICL reacted. 1. That's all I really need in theory. So I got an iodine radical and a chlorine radical. You already know which one of those is more reactive based on when one picks up an H, you get -431. When the other picks up an H, you get -297. Which one's happening a lot faster? We already answered that. -431. So Cl is the more reactive radical. It's taking an H. So here's the 1 Cl dot you've made. The only one. Here's your mole of alkane. Let's pretend we have a mole of alkane and a mole of ICL. Let's just talk about it. Okay? So you removed 1 molecule out of a mole of ICL. How much ICL is left? Just say 1 mole. Okay? 1 out of a mole times 100 is 0.00000000000002%. I had to say 0.21 times. Okay, that's how little 1 molecule out of a mole is. You've reacted none. So the 1 chlorine radical makes 1 HCl, which is one of your products, and this carbon radical. What's the carbon radical going to do? It's going to react with a non-radical, ICL. And it makes 1 molecule of your product. Do these 2 things look familiar? Do these 2 things look familiar? Isn't this the overall reaction that's listed on the top of the page? Well, some of it's listed. I can't see the rest of it, but I see the ICL up there, and I see my box for 3 out of 4 parts. The alkane must be the other one. So what do you call these molecules? Do you want your 3 choices for each molecule? Reactant, product, intermediate. What's this molecule? No, it's not. It's a reactant in this reaction, but when you're a reactant in one reaction and a product in the next one, you're an intermediate. You're never accumulating. Every time you're used, you're made. What do you call this? Now you can say it. Reactant. That's a product. Reactants and products are on the top of the screen. Go a little smaller, we see everything. That did not do what I wanted it to. There. Reactants give products. Got it? Reactants give products. Reactant, product. Reactant, product. What about this? Intermediate. You made it here. You're using it right away here. Students often confuse intermediates with catalysts. What's the only small, there's not much distinction, but there is a small distinction. A catalyst, you go to the stock room and get some and put a little bit of it into your reaction. An intermediate, you are not going to the stock room to get it off the shelf. They are made in one step and used in another. They never came off the shelf. Okay? So yeah, this radical appeared in prop 1 and it's used in prop 2. That's the intermediate. That is a what? It's right there. Reactant, this is a what? It's right here. Product, what's this? Intermediate. Okay, we good? We finished parts A and B. Is there anything else I wanted to say? The overall reaction can be added up. And when you do the overall reaction, you get the two reactants and you get the two products. There you go. That was on the top of the screen. That means if I can figure out the delta H for the two propagation steps, I will figure out the overall reaction. And that's my next activity. So I will stop this one.